Right. What we've got on the right there is a sketch of an exothermic reaction. The work we're going to look at today is bond energy, and we're going to try and link it to the work we did last week, which was on these graphs. So what we're going to be looking at is why is that little hump there? Why does it need energy put in for a reaction to occur? And that is linked very much to this idea of bond energies. You do need to break bonds for chemical reactions to occur. In this case, the energy then released by the new bonds being made is more than the energy we pumped in, which is why it's exothermic. So we need to understand a couple of things. One is why there is even a thing called activation energy, and we can link that to what's called bond energy. Then we can use this idea of a bond energy to work out a value, a mathematical, a numerical number for this thing called enthalpy change, delta H. So those are the two things we're trying to get. The link to activation energy and how we can calculate what the enthalpy change of a reaction is if we know that energy held within each chemical bond. So you might have heard in other years this idea of chemical potential energy, the energy found within chemical bonds. That's exactly what we're looking at, the chemical potential energy. We're disregarding the kinetic energy of the particles because that will be, although there will be a temperature change in the system, that'll be pretty much uniform. Okay, it'll increase or decrease by the same amount for all of the particles, so we can ignore that. So enthalpy change is going to be directly linked to the change in the amount of energy stored in the chemical bonds. If the amount goes down, it'll be exothermic. If the amount goes up, it will be endothermic. So a couple of things you need to just sort of know. One is that to break a chemical bond requires energy, whether it's heat or whatever sort of energy. You need to have some energy input to break a chemical bond. If you want a little catchphrase, breaking up is hard to do. It requires some effort. Okay? So conversely, therefore, when we create chemical bonds, energy is released. And the easy way to think of this is chemical bonds occur to make something more stable, more electrically stable. Well, if it's becoming more stable, then there's going to be energy given away somehow. So it's given off as heat energy, basically. All right, so bond breaking requires energy, so it's endothermic. Bond making is exothermic, so it's a negative value. The delta H is the sum of the bonds made and the bonds broken, keeping in mind that one lot will be positive and one lot will be negative because of this. All right, and that's what we're going to look at. But the first thing we'll look at is this activation energy idea. And that we're going to use the question on page 144 in beginning chemistry. We're going to use 3A, which is this chemical reaction to sort of look at this example. So it's ethene, CH2CH2 plus bromine becoming CH2Br, CH2Br. So it's creating a new chemical, it's a chemical reaction. Now we don't know if this will be endothermic or exothermic. We're also given a whole lot of values for bond enthalpies. I'm not going to write those up on the whiteboard because if you're looking at this at another time, you could look it up online very quickly yourselves. But what I'm going to do is show you why there needs to be an activation energy, why we actually need to put some energy in before this can start to chemically react. And that is because we've got some chemical bonds that we have to break. And the easiest way to show that is to draw these out as structures. Now we are going to get into organic chemistry later in the year, which will help you show these structures better, but we can actually use our Lewis structure rules to draw these. Now we don't need the dots on it, but we can look at the shapes. So if we create CH2CH2, it already shows us the double bond in our book, so we'll draw that in. Well, that carbon's already got two chemical bonds, so therefore the H's must come off like that, and likewise there. The bromine, Br2, is just like this. So I'm looking at what's being added together. When I look at what's made, if there's no double line or anything in between and a carbon can containing compound. It's just got a single line between the carbons. So I just draw it like this. Now I'm just going to fill in the gaps. H, H, Br. Okay, H, H, Br. And same thing on the next one. H, H, Br. Now, I can see that some chemical bonds have had to be broken for this to occur. The chemical bonds that are broken are what is our activation energy. I need to put that much energy in to break those bonds so that this chemical reaction can occur. So that is what activation energy is. If I have a look at this, each carbon has got 2 carbon-hydrogen bonds here, same here. So they get left alone. They don't actually get broken, so I don't actually use those. But I do break this, because a CH bond, sorry, a CC double bond and a CC single bond are different types of bonds. I have to break this one and then remake this one. I'm also breaking this bromine-bromine bond, because notice those bromines are next to each other, but they're not bound to each other anymore. So this is being broken. And I'm making 1, 2 of these CBr bonds. So it's a bit like a balance sheet in economics or accounting. We're just going to add up the stuff that's been broken, because that required some energy, our activation energy. And then we're going to see how much energy we got back by making these 3 chemical bonds. Whichever number is bigger will tell us whether it's exothermic or endothermic. Okay, so let's go through that. On our table, we can see that the CC double bond has got a number 598 next to it. Okay, so it's 598. Now, when I look at a chemical reaction like this, notice that everything has no number in front of it. That means it's effectively 1 of this plus 1 of this makes 1 of this. When we count things in chemistry, we count in a thing called the mole, M-O-L-E. And it's just our counting number. Okay, so I introduced that to you last week, that it was a really big number, 6 times 10 to the power of 23. 6 with 23 zeros after it. It's a massive number. By having this thing called a mole, it's just a bit more meaningful. It just helps us deal with what would be stupid numbers and make them something that our brain can understand. This number, this 598, is how many kilojoules it requires to break 1 mole of these chemical bonds. In a chemical reaction, when I write 1, 1, 1, I don't mean 1 particle. I mean 1 mole. So when I write an equation, this means 1 mole of this plus 1 mole of this makes 1 mole of this. So it means I'm actually not breaking 1 of these bonds, I'm breaking 1 mole of them. Alright, so my unit there is kilojoules per mole. So when you see those tables, that's the unit that we're talking about. I'm also making a Br-Br bond, and according to my table, that is 192 kilojoules per mole. Now, because they're being broken, these are endothermic, so these are positive numbers. Okay, they're positive. Now I'm going to go over here and have a look at the bonds that are being made. And I can see that I've got a carbon-carbon single bond, which is only 346 kilojoules per mole. Notice that this one's a lot higher. What does that suggest about the strength of the double bond versus the single bond? It's stronger, yeah. Now, because this is being made, this is not 346, but it is negative 346. So when I'm adding things up, it's positive, positive, negative. So I'm just going to keep adding these things up. Also, I've got a CBr bond. And according to my table, that's 276 kilojoules per mole. But actually, how many moles, or how many of those bonds do I have in there? 2, so I need to multiply it by 2. And I need to make it negative because they're being made. Cool. So here's where I'm hoping that my maths is good. And it's not. I'm struggling. That's where I need you, please. I've got it as 552. Okay. Now, I can find out how much energy was required to make this reaction occur, the activation energy, as it were. It's not exactly this value, but it's pretty close. That's just adding those two numbers up together. So you can actually do that for us. Yeah?
What about the carbon to hydrogen?
Right, because if they were broken, they've also been remade. Good question. So the question, if it didn't come on the video, was what about CH bonds? Each carbon has got two CH bonds, here and here. So there's no change. Correct. You only look at the bonds that are broken and the bonds that are made. Anything that stays the same, you could include them in your calculations and they'll give you that information in the tables. But I would suggest if you can work out a way to do it without doing all that other maths, you won't make mistakes. Yeah? Any other questions before I move on to the last step? Because this is our last step actually before I leave you to do one yourselves. Okay, so I can find out basically something pretty similar to the activation energy. So I can link it to this. And that's these two numbers added together. So I ignore the ones that are being made at the moment, just the ones being broken. So I can add those up to find my activation energy if I want. But the main thing that I'm trying to get out of this is my overall enthalpy change, my delta H. And all I'm doing for my delta H is adding all of those numbers up that I'm about to underline, keeping in mind the positive and negative symbols. Okay, so I'm just going to add up all of those. It's the sum of these enthalpies. 598 plus 192, I'll need someone to be doing this for me, please, minus 346, because it's exothermic, minus 552. Negative 898? No, that sounds very good. 108, that sounds better. And is it? It's positive, isn't it? No, negative. Yep, cool. And again, don't forget your unit. It's an enthalpy change, so it needs to be in kilojoules per mole. So, would this be an exothermic or an endothermic reaction? Exothermic. How do you know that?
Because it's the change in enthalpy is negative.
Great. And now you can say that the energy released by the bonds being made is greater than the energy being absorbed to break them. Okay, and that's the last bit of our understanding of this, is to be able to write that statement. 1, delta H is negative, so it's exothermic. And number 2, the energy released by the bonds being made is greater than the energy being absorbed to break bonds. So that's also why it's exothermic. Now, just a quick note. In the book, it gives this equation, or something similar to it, that the delta H is the sum of the bonds broken minus the sum of the bonds made. If you're going to use that, that's keeping everything as a positive number. Okay, the minus is accounting for the exothermic aspect of it being made. All right, so the way the book's got it is a little bit different to mine, and both are equally valid. It's either the sum of the bond enthalpy change, okay, so endothermic for being broken, exothermic for being made, or it's this where you keep everything positive, and both ways are equally correct. All right, any questions before I stop this? Awesome.